Chance is everywhere. Despite all the laws of physics, some things simply come down to chance. Statistical mechanics is a branch of physics that applies to the many rather than the few. Usually we talk about one or two objects interacting and can describe the precise circumstances in which they interact. These in turn allow us to develop our models and laws of physics. However, it is an odd observation of the physical world that when you get enough individual objects together, the laws of physics, as they were previously described, no longer apply in the same way. All the multiple variations and tiny amounts of forces and energies acting on individual particles and atoms mean that trying to apply the laws of physics would be pointless. Instead, we use statistical concepts such as averages and variances to describe the physics of the situation. For nuclear decay, we have very many particles working together with a variety of forces making a collection of particles within a nucleus. A real material has billions upon billions of nuclei stuck together in one shape or form. Avogadro's number tells us the number of atoms in a mole of an element. The molar value of an element is the average number of protons and neutrons for that element. The number of protons and neutrons of carbon-12 is 12, so 12 grams of carbon contains Avogadro's number of carbon atoms. 12 grams isn't that much, but it contains roughly 6 by 10 to the 23 atoms. That's 600,000,000,000,000,000,000,000,000,000,000,000 carbon atoms. Or, in other words, 600,000 billion atoms. This is a large number by any measure. Avogadro's number is a basic unit of real chemistry. Chemistry tends to be done in moles, which are a single value of Avogadro's number. It can be seen then that using anything other than statistical rules to do with real atoms would be ridiculous. A real radioactive source, even if it was extremely small, would still contain billions upon billions of nuclei, each with the potential to decay. A radioactive nucleus is unstable. The strong force generated between the protons and neutrons, as well as the electrostatic force between positively charged protons, means that nuclei can become unstable. The larger the nucleus, the more likely it is to fall apart. Although you can be certain that a nucleus will fall apart, you cannot be sure when it will fall apart. It is like a house of cards. The bigger the house of cards, the more likely it is to fall down, but you can never be certain when it will fall down, unless you make it fall down, that is. You can work out a probability for the chances of it falling down, but you can't say exactly when it will fall down. With the billions upon billions of nuclei in a radioactive source, you still cannot tell when an individual nucleus will decay. You can, however, say how much of the overall collection of nuclei will decay in a given time. This is dealt with in the mathematics of nuclear decay.